All right, welcome back. Today, we're going to talk about a super clever technique chemists have up their sleeve. How do you measure a reaction when you can't even see it happening? Well, it turns out it's all about listening for a hidden electrical signal. So really think about this for a second. Imagine you're in the lab, you're mixing two liquids, both totally clear. You know a reaction is supposed to be happening in there. But nothing. There's no color change, no smoke, no fizzing. So how on earth do you know the exact moment it's done? That's the big problem, right? That's what we're tackling today.
For the longest time, the go-to method was pretty straightforward. You just add a chemical indicator, which is basically a special dye that's supposed to change color at exactly the right moment. But here's the thing, and this is what I find so fascinating. This simple solution has a huge fundamental flaw. It relies entirely on something that's, well, notoriously unreliable: our own eyes.
And this slide really just lays it all out, doesn't it? On one side, you've got the old school visual titration. That's where you're squinting at the beaker, asking yourself, wait, did it change color just now? Is that light pink, or is that just the weird lighting in the lab? We've all been there. But then on the other side, you've got the modern answer, potentiometric titration. It just completely takes our flawed human eyes out of the equation and hands the job over to a precise, objective instrument.
So this brings us to the really elegant solution. Instead of looking for a change, we're going to, you could say, listen for one. An electrical one. Yeah, we're literally going to measure the voltage of the solution while the reaction is happening.
So what does that even mean? Well, at its core, potentiometric titration is really just about tracking the voltage of that chemical mix. See, as the reaction goes along, the concentration of the different ions in the solution starts to change. And it's that shift, that change in the ions, that directly changes the solution's electric potential, its voltage. And the best part? We can measure that change with just incredible accuracy.
And honestly, this is the real game changer right here. Because we're measuring voltage directly, we can just completely forget about chemical indicators. Just toss them out. No more guessing about shades of pink or blue. The instrument just gives us a hard number. Simple as that.
Okay, so how exactly does an instrument listen to the voltage? Well, it uses this really clever setup with a two-electrode team, and I love this analogy. Think of them like a news team that's out covering a live breaking story.
So let's break down this news team, right? First up, you've got the indicator electrode. This is your field reporter, plunged right into the middle of the action. Its electrical signal is going crazy, changing constantly as the reaction happens. Then you've got the reference electrode. This is your calm, cool, and collected news anchor back in the studio. Its signal is designed to be totally stable, totally constant. It's our baseline. And finally, you have the potentiometer. That's the control room that's measuring the growing difference between our frantic reporter in the field and our steady anchor in the studio.
Okay, so our control room is getting all these readings. The numbers are coming in. But how do we pinpoint the exact moment the reaction is over? This is where the magic happens. It's a moment called the voltage jump, and trust me, it is the big aha moment of this whole thing.
So to see this jump, here's what we do. We make a really simple graph. On the vertical axis, the y-axis, we're going to plot the voltage that our potentiometer is measuring. And on the horizontal axis, the x-axis, we just track the amount of that chemical that we're slowly adding to our mixture.
Now, as we start adding the chemical, the reaction kicks off, but the concentrations change really slowly at first. So what happens to the voltage? It barely budges. Our graph just kind of putters along, drawing this long, nearly flat line. It's kind of boring. Not much is happening. Yet. But then, bam! All of a sudden, right as the reaction is about to finish, those last few molecules react, and it causes this massive, super fast shift in the ion concentration. And what does that do to the voltage? It shoots straight up. It spikes so dramatically that it creates this nearly vertical line on our graph. That, my friends, is the signal. That's what we've been waiting for. That sharp, vertical jump, that is our endpoint. The exact middle of that spike on the graph tells us, with incredible precision, the exact volume of chemical we needed to finish the reaction. There's no guesswork. No, I think it's done. Just a clear, unmistakable electrical signal that screams, we're done.
So you might be thinking, why go through all this trouble with electrodes and voltmeters and graphs? Well, it's because this method is so much more than just a clever trick. It's an incredibly powerful and versatile tool that solves problems the old way of just looking at it could never even touch.
The advantages are just huge. For one, it's super versatile. It works for all kinds of different reactions, acid-based, redox, you name it. For another thing, like we've been saying, it's totally objective. You get reliable, precise data without any of that indicator error from squinting your eyes. And get this, what if your solution is already, say, dark blue or really cloudy? A color-changing indicator would be totally useless, right? But the electrodes, they don't care what it looks like, they just read the voltage. And to top it all off, the whole thing can be easily automated, making it super efficient.
When you really boil it all down, the true power here is in this one simple but profound shift. It's right there on the slide. It replaces subjective human observation with precise, objective measurement. Just think about that for a second. We're moving away from an interpretation of reality to a direct reading of it. It just completely removes all the guesswork and gives scientists data they can actually trust, every single time.
And that really just leaves us with a final thought, doesn't it? This whole technique is just a perfect example of what happens when we find new ways to measure the world around us. It really makes you wonder, what other incredible breakthroughs are just waiting out there for us, right now, hiding just beyond the limits of what our own eyes can see.